physics. And it's not very usual for us to have speakers who are not exactly astronomers. Actually, Achilleas is not an astronomer. Okay, he's a theoretician doing high energy astrophysics. But this is a rare opportunity for us to have some feedback from people who are not exactly in the community, but nevertheless, what they are going to tell us may give us the opportunity to start collaborating with each other, right? Anyway, Achilleas did his undergrad studies at MIT. Then he moved next door to Harvard for his PhD. Then went to the other side of the US, United States, to Santa Barbara, right? For the first postdoc, and then moved back to the East Coast, Harvard, for the second postdoc, and that was enough. And then he said, okay, this is the time to go back home and do some real good work there. So, as I said, great pleasure for us. Achilleas, so please go ahead.
Thank you.
Talk.
Yes, thank you very much.
You may want to turn off the lights, perhaps.
Sure.
Yeah,
Is that better?
thank you.
Okay, yes. So thank you very much for the kind introduction, the invitation here. It's a great pleasure to talk to you. So indeed, I am not an astrophysicist, so this should be a lot of fun for me, hopefully for you as well. I will talk about things I didn't talk about in the colloquium last week, and they all have to do with observations from the near horizon region of black holes, which are spinning very, very rapidly, and observations in the electromagnetic wind. So one slide before I tell you about the topic of this talk, one slide about the broader research program that I'm involved in. So as I said, I'm studying black holes and ones which are near extremality. I come from a background of high energy theory, where there's been this revolution going by the name of holography, and the purpose of my research was to put holography on your map as well. The route we found is through these black holes, which are spinning very rapidly. Now, I have been calculating a lot of gravitational waves from so-called extreme mass radiation spirals, and I love this topic. I briefly reviewed it during the colloquium last week, but I will not talk about this anymore. Today, I will only tell you about my little excursion into more astrophysical questions, which have to do with optical appearance of sources that are in the electromagnetic. So this talk is all about that topic. Is there a clock here?
I will let you know.
Okay.
It should be.
All right. Okay.
I can always give you some 40 minutes, 50 minutes. Okay.
Great, thanks. So all of astrophysics is done, as far as black holes are concerned, on the phenomenology of this space-time, the Kerr metric. So Roy Kerr found an exact solution of the vacuum Einstein equations. And here is the line. So first of all, it's astonishing that the Einstein equations, a set of nonlinear partial differential equations, can be solved exactly. And you can write down the metric on 2 lines like here.
Yeah, can you take out this thing? There is a
Why is that?
you can adjust so that it doesn't show.
Do you know what?
No, you have to click at the edge and choose that it doesn't show. At the edge of Zoom.
Maybe somewhere
Right
here.
there.
I think it shows up because something is moving. Hide that. Let's see how this goes. Okay, let's hope this doesn't happen. So, okay, so this line element describes all black holes that you guys should care about. All the astrophysical black holes that are out there have only mass and angular momentum. So there are 2 parameters in this metric, m, which is the mass of the black hole, and J, or A, which is the angular momentum. Now, this is as far as gravity is concerned. Of course, you can put matter around this space-time, and you study how it behaves and this background. Now, when I say let's go near extremality, what I mean is that there is this upper bound for how fast the black hole can spin. J must always be less than or equal to m squared. I'm in these units all the time, by the way. When you come close to that bound, or when you saturate it, is when we call the black hole being extreme. You can't go past that. That's the famous cosmic censorship conjecture of Penrose, which unfortunately, or fortunately, depending on your point of view, tells us that there aren't any naked singularities that are not hidden by horizons in the sky. So if there is an event horizon that is shielding any naked singularity, any curvature singularity of this metric, then this bound is such. So let's go to the limit where J is close to m squared. Let's always stay outside the event horizon, of course. And what happens in that limit is that this geometry develops a very long throat towards the horizon. So there's a horizon, and then there's a very long throat that develops when you go close enough to extremality. And this allows you to write down metrics for the space-time near that region, which are independent of this one, and they are exact solutions of the Einstein equations themselves. So they go by these names: neck for near horizon of extreme care, and near neck for the near extreme version of the near horizon care. So this is a bit funny. This is supposed to be meaning near extreme, near horizon of care, or near horizon of near extreme care. So these metrics are describing the space-time near the horizon. But before we write down the metrics, let's look at this picture here. This picture is from a famous paper by Astro people like Tchaikovsky, Bardeen, Press, etc. And this is an embedding of that throat, where the width of that cylinder is the radius. So R plus is, so here are some famous radii. So R naught is just an arbitrary finite radius. And some other famous orbits, okay, I don't know why this is happening again. Some other famous orbits are the horizon, of course, which is called R plus here. The photon orbit, this is the orbit of photons, and now orbit. The marginally bound one will not be that interesting. And the marginally stable orbit is the last circular orbit that time-like particles can move on. So this is what it would be called the ISCO, the innermost stable circular. And then you dial this, you dial the extremality parameter A towards 1, and you go closer and closer to being exactly extreme 1. Let's use kappa to measure the deviation from extremality. So kappa equals 0 is exactly extreme care, and kappa small near extremal. And let's use a dimensional coordinate r as well to denote the distance between r plus and r coordinate distance. As you go close to extremality, two things happen. All of these orbits degenerate in the original coordinates, and they all become equal to just m. That's why this cylinder basically doesn't open up anymore. So all of these orbits are equal to m. But then, of course, they are still distinct orbits, and this throat gets longer and longer. And of course, the innermost stable circular orbit, which is a time-like orbit, it's where a particle could be moving on, remains distinct from the horizon, which is a null surface. So not only that, these remain distinct in the limit, even though the coordinates degenerate, but the proper radial distance between two of these orbits, this is what the cracks are supposed to denote here, goes to infinity. So we have a very long throat, and we have basically infinities here separating various orbits. These are intuitively the reason why you can derive those metrics, which are not care, but they are faithfully describing the near horizon region, and they are solutions of the Einstein equations themselves. So if you go to care and you naively set the extremality parameter to 0, kappa equal to 0, you will get the metric that describes well this region. You would not get the metric that describes well the region which contains the ISCO. because of this infinite proper radial distance. That region is best described by the neck metric, the near horizon of extreme care, which in terms of Boyer-Lindquist coordinates is located at radii which go like kappa to the p, where p is a number less than 1. And if you want to go even closer, if you want to go to r order kappa, come here further closer to the horizon, then the metric becomes this other thing that we call the near horizon of near extreme. So the point of this slide that I want you to remember is that just setting kappa equal to 0 in the care metric only gives you a good description of that region. It doesn't give you a good description of the geometry further closer to the horizon, and in particular of the region where the east is located. All right, so let's see what these metrics look like. So neck, the near horizon of extreme care, which also describes that intermediate region of the near extreme throat, is written down here. So you can see already that this is a simpler metric than care. So that's good. It has also the time translation symmetry and the axis symmetry of care, but it has more symmetry. And the reason it has more symmetry is because this piece here, the RT piece, is ADS2, it's two-dimensional antidesir space, which has an SL2 isometry. So SL2 is an isometry group. Here, what it enhances is basically, so SL2, so the axis symmetry is just a U1, that doesn't help at all. But then the time translation symmetry that care had becomes part of the larger SL2. So it enhances the time translation symmetry, so to speak, and adds 2 more symmetries. We are in particular interested in thinking about this symmetry, the scaling symmetry. So this was not a symmetry of care, but it is a symmetry of this space-time. You can convince yourself by staring at this metric and seeing that this transformation for arbitrary alpha will leave this metric invariant. So there is that scaling symmetry as part of the SL2 associated with that ADS2 factor of that region where the ISCO is located, for example. What does scaling really mean? It means that the physics shouldn't really depend that strongly on what scale you're looking at in terms of radii. So keep that in mind when you see the final outcome of this talk. Okay, the other metric here is the thing that describes the very near horizon region of a near extreme of care, which I don't think I will use much in this talk, but I wanted to display it to you. Okay, so, but that metric also has an SL2 symmetry. This is still ADS2 in different coordinates. And so the point is that the throat of an extreme or a near extreme black hole is governed by this conformal symmetry. SL2 also goes by the name conformal symmetry. And the conformal symmetry has been studied to death in string theory and in modern ADS-CFT because it is on this right-hand side of the duality. So in this talk, I will not use ADS-CFT. There will be no string theory, no supersymmetry, nothing like that. It will be all classical physics. But I will use some techniques and some insights that we learned from studying this duality, and which will enable us to do some calculations here that you would otherwise not expect to be doable. Okay, are there any questions so far? Feel free to interrupt me.
In the previous slide where you showed that the difference, you said something like the proper distance goes to infinity or something like that?
Yeah, so these cracks mean that the proper radial distance goes to infinity. So if you calculate the...
So you cannot move from one...
If this goes to infinity, if you calculate it, say, between, I don't know, R and B and R is... And we move around, right?
But what is the physical meaning of that? That takes infinite amount of time to go from one orbit to the other?
No, what that means physically, well, not very physical, but what that means is that the geometry gets this elongated throat, because this is only radial distance. This is proper radial distance. So what that means is that you have this very long throat, but whether it will take you finite time or not to reach one orbit or the other is a separate question. And indeed, it will take you finite time to plunge from the ISCO to the horizon.
Okay, yeah.
proper time. But this is something that tells you that there is a lot of space-time, so to speak, between those tracks. There's a lot of space-time to feel.
Isco and the horizon are the same values, right? At care maximum spin. I mean, Isco is at horizon, no?
No, that's the thing I'm trying to emphasize here is that
Because
the
there
naive
it is, I mean, the rate is the same, right?
right. So the Boyer-Lindquist coordinate
Yeah.
of the ISCO and of all of these of ISCO, the Poynting orbit,
same.
R plus is just the same. It's
Same,
R
right?
equals.
Which is a physical radius, right?
No. So exactly the opposite. This is what I'm trying to say. Exactly the opposite. If you take that point of view, you're making a fundamental error. Basically, you're telling me that a particle like an iron atom that is orbiting on the ISCO is also orbiting on the horizon.
Well,
But the particle has some mass. It's a time like it follows a time like geodesy. So it cannot be that it's orbiting on the horizon.
I agree.
And in fact, as far as the geometry is concerned, it's orbiting a very long distance from the horizon, the proper radial distance here. In fact, an infinite one because of this crack here. So we really have to be careful. We cannot be using Boyer-Lindquist coordinates if we want to go very close to extremality where this kind of degeneracy happens. The Boyer-Lindquist coordinates are not good coordinates for describing this space-time.
Okay.
In fact, you should use these other space-times, neck and near neck, which faithfully resolve and represent those regions better.
But if the distance is infinite, how can you move from one to the other without breaking a fundamental law in a finite time?
So this is only proper radial distance. If you count the proper time it would take you if you are on a geodesic that plunges through, that can be fine. So the geometry has this, but the geodesic that falls through can still do it in finite time. Defining proper
A
time.
good example is high-dimensional hyperbolic space, where it's infinite volume because of such large distances, but it takes finite time to go to nothing.
Okay, magic. Okay.
Well, yeah, it is a little bit of magic. If you remember that Escher tiling I was showing in the colloquium last week, there were points infinitely far away, and you could keep tiling the thing with smaller and smaller pieces, right? But it was all contained in one small disk.
Okay.
This is another way to see that this funny thing can happen. And this near horizon region behaves similarly. This neck and this near neck have this ADS type structure, which in Euclidean signature is like hyperbolic space.
Okay.
Yes, I know this is all confusing, but precisely because it is confusing, it is interesting. And you're missing a lot of this stuff if you're just thinking of the space-time here, because that's what you're doing when you're using Boyer-Lindquist coordinates only. You're only thinking of that part of the space.
Okay. Thank you.
All right. Good. So, right. So I showed this as my motivation during the colloquium for why I care about highly spinning black holes and why I think they might exist in the sky. So this is a review of what spins have been measured, state of the art as of 2021, and we're told here many accreting supermassive black holes are found rapidly spinning, and the same is true for stellar mass black holes. Now, there's a lot of astrophysics that goes into these claims, and a lot of it I don't understand. But at some point, I wanted to understand how these things are measured and how they derive the spin. So I went in a little bit, and I studied one of the methods they use here, the so-called broadening of iron lines. And I studied it, I think, in this context more. And I redid the calculation myself because I didn't find that the calculations done in the literature satisfactory, precisely because of that problem that they are using degenerate coordinates, basically near the horizon, if the black hole is spinning fast enough. And so this is the main outcome of this talk. Let me also show what their fitting has produced. It has produced this plot for supermassive black holes. And I was happy to see that they are claiming many highly spinning black holes here. This is all done with this X-ray reflection method, broadening of the iron lines. So as far as I understand, the basic thing that is being fit to data is that there are some iron atoms orbiting the black hole in an accretion disk. They are illuminated by the corona or by something, and therefore they transition and then emit line element, line at some energy. And then by the time we observe that line emission, it's being broadened due to relativistic effects and Doppler effects. And that is what we fit, because ISCO is the edge of the accretion disk, and it basically sensitively determines the spin of the black hole. Its location sensitively determines it. We can infer the spin from those calculations. So this is how these points are put here. Now I will do a computation of part of that, just the broadening due to relativistic and Doppler effects. And I will show you that if I already know that the black hole is extreme or near extreme, that calculation simplifies tremendously, becomes a universal result that contains an analytic function. So maybe all of those points can, if they are correctly put there, can be put on a plot of that function. Right. So let me tell you how I understand this. Let me start describing the computations. So this is what I already said. This is what broadening of iron lines means. It's how they measure the spins of supermassive black holes. At the emission point, somewhere near the black hole horizon, say on the ISCO or just outside of it, there is an iron atom. It emits a K alpha line, 6.4, I think, keV roughly. It's a delta function basically at the emission point. It emits some number of photons. Then by the time it reaches us, we are here far from the black hole observing it, this line gets broadened, we get some kind of profile like this, which we, if we can calculate, then we can fit to our data and learn about parameters in the curve, like the spin. So what's the fundamental calculation that is being used here? Photons travel on null geodesics. So fundamentally, what this requires is that we are able to solve for null geodesics, which connect a point very near the horizon, say on the ISCO, to an observatory far out there, far out here where we are in asymptotically flat. That is definitely a big piece of the calculation. We need to be able to find those null geodesics. And therefore, I first studied what happens to null geodesics when they had to reach from NEC, from the near horizon of extreme care, that region where the ISCO is contained in an extreme or near extreme black hole, all the way out to infinity. Infinity being asymptotically far infinity where we are looking. So here are the equations for the null geodesics. So fortunately, there are enough conserved quantities, namely the energy. So the energy of the null geodesic can be scaled away. Therefore, there are two conserved quantities that characterize the null geodesic equations, and we can reduce them to these integrals. They're going by the name Carter's equations, because there is this conserved quantity, the angular momentum, divided by the energy of the point particle. And here I'm rescaling, I'm shifting it to define this lambda. Lambda is basically the angular momentum of the point particle. And then there's this further constant, the Carter constant Q, which roughly speaking measures the energy of that point particle, the photon in our case, away from the equatorial plane. So Q equals 0 is when it is exactly equatorial. But for our calculations, it is convenient to define this quantity here, and I'm going to call it Q squared because it's going to be positive. So basically, these are the equations, and you need to be able to do these integrals to solve for the null geodesics. Now, don't look at many of these things, but take a look at this one, for example. It's telling you the motion of null geodesics in the r theta plane, going from a point near the horizon, that's Rn, all the way to the point far from the horizon, that's Rn. And that function r here, for example, is given by this. So this integral is of elliptic type, and you cannot write down a formula for it, a formula that is analytic, but you can evaluate it numerically, and that's what nearly everyone does. And you have to do it in the generic case. But if you know that the source, this Rn is in the neck region, you can do an analytic calculation where you do an approximation using this so-called method of matched asymptotic expansions to write down the solution of the null geodesic within neck, basically, and then glue it onto a solution in the outside region. So let me review a little bit how that goes. Basically, the method is like this: matched asymptotic expansions. How it's done? You are solving an ODE, or you're doing a one-dimensional integral on, say, some line X, and there's a small parameter, let's call it K, in the problem. And if there is such a small parameter, then you can define two regions. One near region, where if you're able to find a near solution, that's great. That will be the neck region for us. And you have another far region, which is defined as X much greater than K. If you're able to solve in that region as well, then you're in business. Why? Because K is a small number, and therefore there is an overlapping region. There is a region where X is simultaneously greater than K and less than 1. And in that region, you can match the two solutions. You can identify the integration constant, for example, with those integrals and do it. So applying this method for, say, this integral of the null geodesic equations from neck all the way to infinity, we can look at this expression here. I should first say that a null geodesic that reaches all the way deep into neck will have lambda being much less than 1. So this is a small parameter. So null geodesics which don't have such angular momenta close to this so-called subterranean bound, energy minus horizon speed times angular momentum much less than 1. Null geodesics which don't satisfy this, they don't have a profile within neck, basically. They don't come in and have some trajectory within neck. They zoom through it. But if they do have this, then there is a null geodesic in neck, and you can solve this integral, for example, in this near region, the neck region, by making the approximation that R is much less than 1. Then you drop these terms, and the rest is a quadratic, and so you can integrate. This is an elementary integral. Similarly, in this region where R is much greater than square root of lambda, you still get an elementary integral because you have this R times, again, a square root of the quadratic. In that case, R much greater than lambda, what is being dropped is this term here and this term here. So the last two terms are being dropped, and R far is approximated by this equation. So now you have these two, you have an overlapping region, and so you can do matching. You can do this matched asymptotic expansions and find an expression for this integral to lead in order in lambda. So this is how you calculate null geodesics that are originating from the neck region, or the near horizon, and reaching all the way to asymptotically flat. Let me make also this one point here, that in the far region, we want to have no radial turning point. Why is that? Because we want the null geodesics, if I shoot a null geodesic from infinity, I don't want it to hit a turning point and come back to me. I want it to go all the way and reach that near horizon source in order to measure something, right? So I don't want a radial turning point, and that means that this thing under the square root there should have no zeros, and this leads to this constant q squared always being positive. That's why it was called q squared. Okay. That will be useful in a little bit, I think. Yes, right now. So the simplest thing you can do once you understand how null geodesics behave is imagine that you have a lot of light coming from behind the black hole and doing something in the vicinity of it and coming back to us on our screen and producing the silhouette of the black hole. So this is not what the kind of thing that the EHT measures. This is a simplified version of what the EHT would measure. If all of the sources were very bright and they were all between us or behind the black hole as far as our line of sight is concerned, then we would get just the silhouette. So this region would be completely dark, and the edge of it would be the silhouette.
I'm sorry, what is the viewing angle here?
So the viewing angle here is theta naught. Is denoted by theta naught. So okay, let's.
But it can't be the same if it's 0 or if it is 89 degrees.
Yeah, those cases are a bit degenerate in these coordinates. Let's not think that theta naught is one of those two. If they're not one of those two, then alpha and beta are good Cartesian coordinates on our screen. And they are related to theta naught. Alpha is related to theta naught by this equation here.
Basically, what you plot here is as ISCO. That's what you're plotting here. Because you have no radiation, you have no photons. What do you plot here? Is it ISCO? How ISCO is going to look on our screen?
It's not necessarily just ISCO. It's because so it depends on. Okay, so
You
two
don't
things.
put photons here.
There are photons that are coming in from behind the black
But
hole.
from in front as well.
I'm ignoring that. This is a simplified calculation where I'm not doing it.
So where are the photons on that frame, on the black hole frame? Just 1 point from the back. Where
Yes,
do
all of the photons
come?
are supposedly in this idealized situation are supposedly coming from one very bright source behind the black hole,
Which is point light.
which may be point light, yeah, or maybe an entire plane that illuminates everything. This is making it as simple as simple an image as possible.
Like or plane, it can't be the same. Because plane will go below when you have emission from above and below the black hole. It will not be just a point light. It can't be the same. You will not see the same image.
What do you mean by the same image?
It can't be the same if it is a point light or if it's a plane. The dark thing, it can't be the same.
No. If there is enough light
Yeah.
behind the black hole, such that I can ignore everything else, everything coming from the accretion disk, everything coming from other sources. If there is enough light from behind, such that it will illuminate the thing as much as possible, there will be an edge to the picture.
Okay.
Right, and that edge will be somewhere. Now, I understand that if there is some anisotropy and you illuminate a little bit from one side and less from the other side, then the picture will change. What I'm trying to say here is imagine the most idealized situation where we have an infinite amount of light sources behind the black hole, which is shining all the way towards us. And in between us, there is only the black hole because we can ignore everything else. What is our screen going to look like? It will be just the shadow of that black hole, basically. And it will look something like this. The fact that it is like a pancake rather than a circle has to do with the fact that the black hole is rotating. But the thing I want to emphasize here is that if the black hole is rotating very fast, if it's nearly extremal, then the null geodesics which will explore that neck region, the near horizon region, will all be coming and hitting only this piece of the shadow. So some null geodesics will not explore the near horizon region. They will come around from other places, and they will land on other parts of this silhouette. But the ones that will be passing through the neck region and coming to us, they will all land on this little piece here, which is actually vertical. It's exactly vertical in the exactly extremal limit, and this is because of this condition that lambda is much less than 1. So lambda is much less than 1. It translates in this alpha beta coordinates of our screen to sitting here as specific alpha. And then this other condition that q squared has to be positive for us to connect those geodesics between near region and us. This condition becomes this one here, which tells you that this vertical line, has a maximum and a minimum beta coordinate. So that's point 1. If you are observing an exactly extremal or a very nearly extremal black hole like that, its silhouette should be like this in general, but the part from the near horizon region, any emission from the near horizon region, or any null trajectory that passed through that near horizon region and ended up on this screen, will always land on this piece of the silhouette. We call this the neckline. Okay, are there any questions? That's surprising and maybe unusual, but this is what happens if the black hole is extreme.
these coordinates have any relation to the plane of the sky or not?
These are the Cartesian coordinates in the plane of the sky in the asymptotic Planck region. This is the coordinates you will use on our telescope.
Okay, so
Cartesian
and the asymmetry is related to the spin you said. So you have something which is spinning along the beta axis right now.
So no. So we have a line of sight which has an angle theta naught. So it could be spinning on any axis as far as we're concerned. But the point here is perpendicular, I think, to theta naught, if I remember the equations correctly. I think this center here is let's see, this center here is the one where you would draw a perpendicular, which would be our line of sight versus the black hole. Is that right? Yeah. Okay. I think so. Yeah. We could look at the equations again, but these are not difficult to write down because they are Cartesian coordinates in flat space-time, basically. So you do a little bit of flat space-time geometry with a line of sight that's at theta O, and I think you put the center here, and that's how you observe the black hole. I mean, there isn't anything else on the plot, so it has to be that.
Okay.
Okay. So we're not, what I'm trying to say is that we're not observing the black hole here from the axis, we're observing anywhere, but it always comes out like that. Pancake.
So theta zero is the angle between what and what?
Theta zero is the line of sight that we have, our screen has versus the axis of the spin of the black hole. So we're not looking at the black hole, down the barrel. Basically, we could be looking at it like that, and our screen would be then this alpha beta plane, which would produce this image. All right. So that's the first point. That extreme black holes look very different, and the emissions from the very near horizon region all end up on that little piece, the neckline.
And as you make the black hole less extreme, it becomes more circular.
As you make the black hole less extreme, this becomes more circular, and this becomes less vertical. Yeah. And also grows in size. Basically, what I'm saying here, there is a beta max, given by this. This also grows in size.
Grows in size, but becomes less vertical.
Becomes less vertical. So you basically make it more. You make this picture approach a circle,
okay,
and then the near horizon part begins to land on more of this circle.
Okay.
So if you have a structured black hole, you can have emissions from the near horizon region land anywhere on the circle that will be the shadow of the structured black hole. But for an exactly external black hole, it's not like that. The near horizon emissions all land on such a piece, which is also vertical. And it has some finite size given by this equation. All right. Yes, so that's the neckline. Now let's talk about that broadening of iron line calculation. How much time do you have?
So you've got 10, 15 minutes.
10-15 minutes. Okay. This will be a little fast, but okay. So let me tell you how that calculation goes. So what is being calculated? So people are doing basically ray tracing. They're tracing those now geodesics and collecting the energy. So this ray tracing allows you to calculate observables such as fluxes, for example, by using geometric constants. So if you have now geodesics which subtend a solid angle d omega on your screen, then the flux df observed that is being measured is given by this equation here, where g is the redshift of the photons, so energy observed divided by energy emitted in the rest frame of the emitter, and IE is here the emitted specific intensity at the emission point. So roughly speaking, d omega is general relativity. D omega is how these now geodesics are connecting the 2 points, whereas the specific intensity is astrophysics. You need to know a lot of astrophysics to find out what IE is, what the emission is. So I think this is messy and the general relativity is clean, but that's maybe because I'm relatively ignorant about a lot of astrophysics. Good. So now, what is a calculation that can be done? So suppose we consider a stationary, axisymmetric, slowly accreting thin disk. So these are some assumptions that are relatively standard, although there are models which violate those as well. And it contains emitters, which are traveling on circular orbits on the equatorial plane. Let's assume that the only emitters we deal with are these iron atoms. And so we have monochromatic energy, E star here, which is that K alpha line of the iron atom, the 638 kV. Therefore, I'm making this assumption that the specific intensity here is given by an equation like this. It's a delta function at that energy, and there is some surface emissivity function curly epsilon of Re, which I don't know, and what it measures is it basically tells me how many of those atoms I have as I move across along the accretion disk from, say, the ISCO all the way to wherever they still exist. So I need to know a lot of physics to know what this function is. I need to know if there are these things out there in the sky, how many there are, and what determines the density as you move up. So many of the original, at least, measurements of spins just assume that this is some kind of power law drop. So they took this function to be r to the -3, r to the -2, and they tried to fit the data. If it didn't fit the data very well, they broke it and they make it two power laws, r to the -2 and then r to the -3, etc. But there are more sophisticated methods. If you use this Novikov-Thorne model of the accretion disk, you can write down something more interesting about this function. But the point being here is that this function is difficult to know. You have to know there's a lot of astrophysics, and you have to know what is going on as far as matter is concerned near the horizon. Okay. Now, fortunately, I will not need to know what that function is in the end. Now let's look at the other piece, the solid angle subtended. D omega. So if we are at a distance large d from the black hole, this is just d alpha d beta. That's the Cartesian coordinates on our screen. So d omega is this. And then what you would do is you would try to transform from alpha beta to R, E, and G expression such that you can integrate this delta function of G to set to do one of the two integrals and set the energy observed to this redshift. So how do you do that? You do it in two steps. You go from alpha beta to these conserved quantities of your nodular physics, lambda and q. So this is the first Jacobian here. And then you go from lambda and q to R, E, and G. So you should think of this now as telling you what kind of nodular physics with which conserved quantities lambda and q, what angular momentum and what Carter constant, will connect a point that is a source that is emitting a photon at radius r emission, and with redshift g by the time we get to observe. All right. So the other thing here, the other thing is easy because that thing we can do near our screen, near flat infinity. This is going from Cartesian coordinates, but also using conserved quantities of the geodesics near flat infinity. This is the more difficult Jacobian because that has to do with a point of emission where gravity is strong and null geodesics are doing difficult things. So that's difficult to compute, but we have already learned a little bit how to compute those. In the end, if you plug in this expression here together with this into our formula for computing the flux, and you integrate dg, the dg integral is trivial, you get an expression of this type. So the observed flux, the number of photons that you're collecting, is some integral, some radial integral, dg has disappeared, of basically this Jacobian here. The hats here are meant to imply that I'm using original, say, Boyer-Lindquist coordinates, and this formula is applicable for a generic here. I'm not using the coordinates appropriate for next year. Now, this integral is supposed to be happening over the extent of your accretion disk, wherever this function is not zero, typically starting from the A score. But in some other models, they incorporate more than this. Now, what is standing between us and calculating this expression? Two things. So one thing is that we don't have a way to analytically, for generic care, we don't have a way to analytically compute Q in terms of RE and G. So that is a difficult question. Lambda is easier to compute in terms of RE and G, although I will not have time to explain how. But Q is particularly difficult. Q really requires you to have solved the R theta motion of the non-geodesics and inverted it for Q. And the other thing that stands between us and doing this integral is that we don't know what this function really is. Or at least I don't know what this function is. And there are competing models for what it could be. But when the black hole is extremal or near extremal, and we consider sources RE which are in that neck region, these two problems are solved, both of them simultaneously. And the key insight is that for a fixed G, the dominant contribution to the flux is coming from sources which are at radius RE, which are such that when the non-geodesic is being emitted, the dominant contribution is coming from those geodesics with lambda and Q, with angular momentum and Kuiper constant, such that the point RE is a radial turning point of that neck geodesic equation. So that's the main key insight. So if the most of the contribution to the flux is coming from wherever that near expression of the radial integral is zero. So this dramatically simplifies things and allows you to compute Q in terms of RE and G. And then what happens is that, moreover, this Q does not depend on RE at all. And the entire Jacobian here, the thing that sits here, is also only dependent on the redshift G. So in the end, this integral that you would have to do numerically with an unknown function here basically factorizes into an expression like this. You have one function of G, which you know, because these are some trivial calculations here, which you know, times an integral of the unknown emissivity function. So this kind of factorization perhaps should have been expected because of the scaling symmetry. So remember early on, I told you that near horizon region of a nearly extreme black hole has a scaling symmetry, which means that different radii are not physically that different. I can rescale the radius and it's a symmetry. So it shouldn't, therefore, it shouldn't matter very much. This dr integral shouldn't be consequential. And this is indeed what this factorization turns out to show. That basically, I'm just adding that emissivity up, and the observed flux in terms of redshift is another function, depends on G, which I can now compute analytically, and here it is. So this is the surprising part, that for extreme and near extreme black holes, the observed the broadening of the iron line should follow this curve here, and it's an exact analytic equation that we can attempt to fit to the data if we have enough near extreme black holes. And the other things I want to point out here. So this is an overall thing that I don't know and I don't care most of the time. The other thing I want to point out here is that the angle that this radiation comes out in is always between a critical angle here, 47 degrees, and pi minus 47. And the redshift that is being observed is always in this range as well. So this is another outcome that is also due to this extremality thing. This I already explained. This was because of Q squared being positive. This is just coming out of the calculation. So I'm going to end here. Let you appreciate this formula. Thank you.
Any questions?
Just naive questions.
Another question. So the astronomers that interpret the broadening of the line with whatever tools they're using, are they doing it wrong? Because they infer high spin.
Yeah. Are they doing it wrong? So, frankly, I mean, if we want to be strict, they are probably doing it wrong. Yes, they're using naive equations. They are fitting with equations that come out from the Boyer-Lindquist calculation. They are ignoring all this near horizon region. They're assuming that basically it all comes onto the horizon. So yes, I think they are wrong. Yeah. So if there are very highly spinning black holes, which they do claim that there are, then the calculation that is correct will produce this curve, and they basically replace all of that curve with a number. So in that sense, it is very wrong.
So if you were going to plot the spectrum, like including the redshift of each photon, you would get a spectrum. So if you were going to plot the resulting spectrum from this equation, how would it look like?
Well,
that's $1 million question for us. I mean, would it look like the spectrum that we are using for inferring the spin, or it would look very different?
A similar question, just for you to understand. If you go back where you show the line, which has an energy of 6.38 kJ, right? Okay.
You mean this? Schematic?
Yeah.
Okay.
So this is in the rest frame.
This is in the rest.
What are we going to observe for that line? With your method?
Yeah, so I guess that's the same question. What does the curve look like? Does it look like this or not?
Because that's crucial. That's what we see. Right?
Yeah, but before we go there, we have to. It's not going to be that kind of curve, because it is also so that we also have to understand the amplitude. It might be a little bump on top of that type of curve. Now, so what do you want to know if the function that I wrote down here looks like that curve or not?
Yeah, right. First of all, you have it as a function of G. Where is energy here?
G is the energy. G is the rest.
So if this is the energy, right? Okay. Just show us what would be that at infinity for different values of the spin.
Yeah, I could plot this, yes, and look at it. But there are more things to worry about before we try to fit data, basically. One is
it would be interesting.
They don't ask you to fit data, they ask you what does it look like.
And in fact, what is the difference between what we are doing at the moment when we're using the normal coordinates?
But this is
Why
only
is
for,
it different?
isn't this only for the exchange region? Whereas you also observe.
right. There are several things to do in addition. So this is the contribution.
In fact, which is precisely before this there.
Okay.
You get light. That's all of the light that we get here comes from linear horizon region.
No, so that's one of the
So
questions.
how do you separate the two? And which is important and which is not important?
Yes,
That's what we discussed here.
hard to know. Yes, I don't have a good answer to that question. So this is the contribution that is due to the region that is well described by that metric. But the accretion disk likely extends beyond that. And whether the contribution from there is comparable to this or not is a difficult question that I have not managed to understand.
That's not that.
That's one.
That's not that difficult. But we can discuss it
Okay.
later if you want.
The other question is, so here I didn't put, so this is an integral which is supposed to start from the ISCO and go all the way to wherever the approximation begins to break down. But in those near extremal limits, this will give some small numbers, because those radii are basically all clumped onto this R equals N, right? So it will give us some small numbers, which could suppress this entire function to being a small bump on top of a larger chain. That's the other thing to worry about. That is on the one hand. On the other hand, if you decide that you want to fill in the throat along proper radial distances with sources, per unit proper radial distance, then this integral would also logarithmically diverge. So you have a small number multiplying this logarithmically diverging integral. And I don't know whether the answer is finite or not, or
This divergence comes from.
this divergence comes from this divergence here. So I'm saying if you decide that there are sources that are arranged pair radial, proper radial distance in the throat, then because the proper radial distance of the throat is infinite.
In fact, physics is telling you that this integral should be finite, so you should adjust epsilon so it is finite, right?
Yeah, I mean we can do a cutoff for near extrema one, but what I'm saying is that it's going to be a large.
You do a cutoff, but epsilon as a function of array should be integral.
In the near extremal case, yes, but it's still. I mean, if the exact extremal one is a logarithm, as I'm saying, it will be a relatively large number.
Why it should be a logarithm?
Oh, because it is a logarithm like this. This is a logarithm. The way this the divergence is a logarithm.
Density. You're integrating the density, not the distance.
What I'm saying is that one of the most, one of the assumptions I would like to make for assuming what this function is that I put one iron atom per proper radial distance.
Wrong.
Well, maybe you think it's wrong, but on the other hand, it seems to be like the only.
It's wrong.
It's only the only reasonable assumption that will respect the symmetry.
Forget about that. Because what we're doing here, it's not physical. So exactly as you said, there is illumination. So you have to think of a source that illuminates. You have the geometry. So now you know that how much X-rays are going to each part of your case. And that this is not whatever you want. This has physics and it depends on your geometry. So forget about that.
Well, I agree that it's not whatever I want. But it's also not that there is a simple answer to what this is.
Yes, there is. You can test hypothesis.
Yeah, you can test hypothesis. But when I went into the literature and saw what they are using for this function to actually infer those measurements of the spins, some of them use just a power law drop-off here, which is wrong. You would say
it's absolutely wrong. Yeah,
it's absolutely wrong. I agree. But then some other people will say that even Novikov Thorne is not the best thing to use to derive this function, right? Isn't this nice that it doesn't really matter? The G dependence will be this universal thing, no matter what your epsilon is. I think that's the interesting key. If the black hole is near extremal, whatever this epsilon is, there will be a universal overall function.
If we can observe.
Ultimately, yes. Okay, sure. Yeah.
I was wondering, I mean, because I also agree that the astrophysics is messy, can you give me a contribution for the something like a Shapiro delay for this?
I'm sorry, what I don't understand.
Like, say if you have some other source like the contribution to the light travel time, let's say, from the extreme, the deviation, I'll see.
So if you don't want to go into messy astrophysics, I think this is the cleanest signal that you can talk about. So this is not making any assumptions about, what kind of photons reach you. It's assuming that there's an infinite amount of them, and they are coming from behind the black hole, and because the black hole is curving their orbits, they come and hit our screen and produce this silhouette.
Okay, but in order to get this, you need this special coordinate.
In order to produce the right plot for the case where the black hole is near the extremal, you need to use the correct near horizon coordinates to realize that this part here is vertical and it's coming out from the near horizon region, etc., etc.
What would you get if you use naive as per order?
Yeah, I mean, that's what I was trying to do.
Well, the frank answer is that you're doing the calculation wrong, so you're getting garbage. But
No. But what's the difference? The garbage compared to this?
Yeah.
That's the question.
Because that's also like
Because if the super is garbage, it has to be different. Because maybe the calculation is wrong, but the result is right.
Okay. Okay, roughly speaking, all of the pictures look like this. So even if you do the calculation the wrong way, so to speak, the silhouette will look roughly like this. The only things that will differ is that this may not be exactly vertical, but mostly you will not be able to identify that now geodesics which reached you from the east coast, let's say, are landing here. You will be thinking that they're landing everywhere. Just like now geodesics which are coming from further away from the black hole. Yeah.
But my
They are landing everywhere else.
It's an important question to do a detailed calculation in a traditional way,
Yeah.
and compare in a
And compare.
detailed way with this one,
Yeah,
and estimate the difference.
yeah, I think
Because maybe it doesn't make any difference, then what's the point?
no, the point is that we will never be able
Now,
to
if
prove
you
it.
want to scaling.
Yeah,
But if there is,
Yes.
we will never be able to prove it.
Right, you want to know, is it dramatic, is the picture dramatically different? No, it's not dramatically different. It always
So
looks
it will
roughly
be
like.
very hard to.
Right, it's very hard to see whether this line is exactly vertical or not, and etc.
So it will be very hard.
This is hard, yes. And of course, this is still, this is anyway an idealized situation. This is just a silhouette. We don't observe black holes or illuminated like that, right? We observe what the EHT measure is not this. It's not the silhouette. Most of the contributions that the photons that EHT measured were coming from the accretion disk, basically from the area near the horizon. They were not measuring photons that were all coming from behind the black hole and trumping everything else.
So is it unthinkable to imagine that for such a near external black hole, only indication which the accretion disk is really inside the near horizon region, you would expect a substantial signal of this scale?
Well, first of all, it is definitely true that part of the accretion disk reaches the near horizon region because the near horizon region, the ISCO is deep into the neck region. This is where the ISCO is, and you can't say that there is no accretion disk here. So there is always part of the accretion disk that is in the region that is governed by this. The question is this a dominant contribution? How does it compare to what you get from there, etc.? So yeah, I mean that's again a question that I don't have an answer to. I don't know the answer. I mean, these are all questions which are very good and should be answered, and probably are answerable. I mean, they're not questions which could not be answered.
Yeah,
but they're not so easy, and I haven't investigated.
Is there any reason why the emission from the near horizon region is suppressed?
So there is a reason, and that's because redshift, right? Because gravitational redshift. So it is suppressed on the one hand side. But then on the other side, because the black hole is spinning very fast, there is the countering effect of the Doppler shift, which is competing with it. And therefore you could get a finite outcome even from that deep region.
Near the black hole rather than far.
That is an assumption that I don't know if I am eligible to make.
What do the astrophysicists?
I don't know.
So, I mean, I think
things.
we should, at this point, finish it off and perhaps we can discuss, people who are interested. I don't know if there are any questions from the audience of the,
The Zoom.
from the Zoom. I don't know if they have raised their hands or,
Let's see.
if not, then I think we should.
Okay. How do we know if there
If there are any hands.
I don't see any here.
So, okay,
Okay.
right, so let's thank the speaker.